All right, dudes and dudettes, look up here for me. So this is your worksheet. You guys have it in front of you as well. I'm going to get some volunteers to help me with the first part. So in Model 1, it gives us the different masses of the different water samples. The rate of heating is 30 joules per minute, right? And they both increase, or they're both being heated for the same amount of time at 5 minutes. And now that back table back there. Okay, you can tell me number 1, which container holds more grams of water? The stock pot versus the saucepan, right? The stock pot, 8 quarts. Okay, let's go ahead and move to part 2. How many joules of energy were added to the saucepan? Same team back there. Say again? How did you get 150? So you're just, and I can't run on smartboard because it's being dealt with PDF on this one, so you're doing 5 minutes. You're basically doing dimensional analysis, but you just don't realize you're doing it likely. But it's 30 joules per 1 minute. And so for 5 minutes it's heating, so the minutes cancel, it gives you 150 joules, right? So table up here, Gray's table. How many joules of energy were added to the stock pot? 150, yeah, again, because we're doing the same process, heating over the same amount of time. So the same energy was applied to both of them, right? So in which container did the liquid gain more energy, or did they both gain the same amount of energy? What do you guys think up here? So they gain the same amount of energy because the joules, quantity of the joules was exactly the same. But for each container, include whether the temperature is expected to increase, decrease, or remain the same after heating. Explain your reasoning. This is probably the challenging one, but Haley's table, what do you guys think? For D.
Consider like increase because like it had more energy in it.
Okay. So it says for each container, include whether the temperature is expected to increase. So you're saying both containers are increasing in temperature. On the kind of foreshadowing this, do you think that they increase by the same amount of temperature? Likely not. Why? Okay, so the energy that was applied, that 150 joules, was applied to a little pot versus a big pot, right? So the small saucepan kind of had a small amount of volume to heat up, maybe increase its temperature more versus a larger pan. Where could that be applied in real life? What large body of water is constantly heated? The ocean, right? If it was a small, like a cup of water sitting out like on a beach someplace, the water bottle is going to get pretty hot pretty quick. But the ocean doesn't increase its temperature much at all, maybe a little bit over the course of a couple months, but not much at all because it's such a large body of water. It's going to take a long time to diffuse that energy throughout the large body. All right, next one. So we have this data information, all this data, and then we have some questions afterwards. In the data tables, what does delta T mean? CJ's group. Right, so in temperature change is calculated how, Abby? We do something minus something. We always do one thing first and the other thing second. Your group. Right, so T final minus T initial. So temperature final minus temperature initial. And so they don't show that here, but that's what they've done here. All right, which experiment illustrates how much energy is needed to achieve the same temperature change temperature change depends on the mass of the water. So which experiment did you guys say, this kind of clumped up area here? So experiment 3, and you're seeing that because the mass of water is different and the temperature change is staying the same throughout, and you can look at the energy is different there. And so question 5, which experiment illustrates how different amounts of energy will result in the temperature? Riley's group. Experiment 2, so you're looking at the constant here of mass and how the differences in energy and temperature are correlated despite the fact that we have the same mass. And then on the last bit, why was it necessary to perform 3 experiments to find the relationships between mass, temperature change, and energy? Amaya's area. Why was it necessary for us to do this? 3 experiments to see the relationships between them all. Amaya's group. You got some people there.
To like keep things constant so we can see how they affect other things.
Okay, so what is that in a typical experiment? What is that called? So kind of a control, or it can be called a constant variable, actually a constant variable. So if I was doing an experiment on you guys, I would have to keep many of the conditions constant, like your rotating groups, remember that? Your rotating groups weekly, so I can make sure that the one thing I was changing was actually being measured by the results you guys had on your Cornell test and stuff. Huh?
What are you trying to study there?
Effective collaboration strategies, which I haven't found out anything yet. I'm still data crunching. I submitted my data about, probably 5,000, like 15,000 data points to my teacher. And she's helping close to that because there was more than me in the study. And one line of our data is off. We have to go figure out which line of data it is. I just found that out yesterday, and I was like, oh my god, I'm gonna die. Okay, so I gotta figure out. Yeah. Figure out because like something doesn't align. I was like, no. So we have to do like statistics on everything. So anyway, so let's talk about the relationships of the variables that these experiments kind of included. So what were the 4 variables that they related? Give me one of them.
Mass, change in temperature.
Mass, change in temperature. Joules. Okay, so I'm gonna call that Q. They didn't say the other one, but I'll tell you that they're talking about water, one particular substance through this entire experiment so far. But there is something called the C value, the specific heat capacity. It's different for every type of compound out there, so that's going to be another variable we'll consider. So, which of the variables do we already know are related? All right, tell me how they're related. So, for example, I think it was question 7. When the amount of energy is added to water samples of different masses, the change in the temperature gets blank when the mass of the water increases. What did you guys say? You guys said smaller. So what's the relationship between mass and temperature? Inversely related. As the mass goes down, the temperature goes up. Just like the saucepan had a small mass, the stock pan had a large mass, the temperature differences would be related in this manner. And then question 8, describe the relationship between the observed temperature change and the energy required to heat the same amount of mass of water. Anybody? Temperature and energy. Are they those two related? Those are directly related. So as you increase the as you increase the energy added, the temperature should increase. So what we're going to start to do is think about, just like we did with our gases, how are things related, and then how do they relate in an equation as well. All right, so I think you guys are going to fly through this today. I think, because you got a good intro to it yesterday. So put the warm-up away. Let's watch one of the videos together versus you watching it on your own. And so the video I'm doing is the first link where it says heat exchange. I want you to write this down someplace on a separate sheet of paper. Write down 5 things he says, 5 things you learned, 5 things that you think are important. Not on your warm-up sheet is fine, just not on your colorful sheet of paper yet. So writing down 5 things. We cut off Pandora. Is Pandora on?
Hi, it's Mr. Anderson, and this is Chemistry Essentials video 47. It's on heat exchange. If I were to say, don't touch this iron right here in the middle, it's hot. What does that mean? Well, we know that it has a higher temperature, and therefore it has a higher amount of average kinetic energy. And if you were to touch it, a lot of that energy is going to be transferred to your hand, and that's going to produce quite a bit of pain. And so if we ever have a warmer body and a colder body, the warmer body is going to have more kinetic energy. And again, that energy is in the molecular motion, or those molecules moving around. And we're going to have more energy in that than the colder body. And so a good way to represent that, and I'll use this model over the next few videos, is just using these little cubes that represent the amount of energy. In this case, that's going to be thermal energy. And so if I were to put those 2 objects in contact with one another, that energy is going to be transferred. In other words, energy is moving from that first object to that second object, and we call that transfer heat. And so what we're really doing is transferring energy as thermal energy, or heat. Now heat, if you were to look up heat on the periodic table, you're simply not going to find it there because it's not a substance, it's not a thing, it's just the transfer of energy. And so a good way to think about that, and this should be a sentence that should kind of roll off your tongue, energy is being transferred as heat. That's really what's going on. And so when we're looking at energy being transferred as heat, it's going to vary depending on the substance that we're dealing with. In other words, metals are going to transfer energy through heat more readily than things like wood or brick. So let's look at this PHET simulation. So I've got iron, I've got brick, and then I've got water. And so we can assume that we have the same amount of each of these. And if I were to put the water on top of a heating device and the iron on top of a heating device, and I were to just increase the amount of energy, what I'm going to see is an increase in temperature. Well, what's really going on is that we're speeding up those molecules. That's speeding up the molecules of the thermometer. It's spreading apart. Likewise, when we cool it down, what we're doing is we're cooling down those molecules, cooling down the molecules of the thermometer, and therefore it's going down.
So the thermometers work simply because there's heat or there's energy transferred to it or from it. It's not like some magical device that's like, it's measuring temperature. It's actually measuring heat exchange, which influences that little liquid on the inside. So he's going to tell you a little bit more about the differences between these materials. That's the only part we've not really expressed yet.
But we really don't see that energy transfer as heat. And so now what we're going to do is we're going to click on the energy symbols button. And now we're actually going to see that energy inside those molecules. Now as I'm heating it up, what's really happening is I'm adding energy. I'm adding energy to that iron. Now you can see that some of it is being transferred out to the environment through heat. Likewise, when I cool it down, what I'm doing is I'm actually transferring that energy as heat into the ice cubes. So they have lower kinetic energy. What happens if I take that iron and I just throw it into the water? You can see that since it's hotter, it's transferring some of that energy as heat as well to the surroundings until it eventually reaches what we call equilibrium. And so if you ever have a warmer and a colder body, that warmer body is going to have a higher amount of average kinetic energy. Remember the Maxwell-Boltzmann distribution shows us how that works. If we were to look at it, this would be the cold body and this would be the warm body. Now in each of those bodies, they're going to have low energy particles and really high energy particles. But in the warmer body, that average kinetic energy is going to be greater. And so if we ever put them in contact with another, there's going to be a lot of collisions between these molecules. And as they collide, they're transferring some of that kinetic energy. And so what we're really doing is we're transferring energy from the warmer object to the colder object through heat until they eventually reach what we call thermal equilibrium. In other words, it's the same average kinetic energy on both sides. And that picture I showed you of iron at the beginning, eventually what's going to happen is all of that iron is going to have the same amount of kinetic energy because we've transferred that energy out. Now, it's not the same for every substance, and so we use a term called specific heat capacity to measure that. And so right here, you can imagine we have a kilogram of gold, a kilogram of aluminum, and a kilogram of water. And let's say that they're all in a container. And so if you look at it, they're going to have different amounts of specific heat capacity. If we look at the units, that's joules, which is a way that we measure energy per gram, and then Kelvin or degree Kelvin. And so if you have something that has low specific heat capacity, that means it's going to be changed, the amount of energy it has is going to change more readily than something that has a higher specific heat capacity. So let's add a little bit of heat to this and watch what happens to the thermometers. And so the gold, the aluminum are heating up more readily than the water.
All right, so can somebody explain that reasoning behind that for me? So you kind of explained a little bit, and then you can see the temperature of gold raises very quickly, and water not as quite as much. Can I get a volunteer to help me out here? Put it in your own words. Katie.
Because
Okay, so the more joules it takes to put in based on the specific heat capacity value, the longer it takes to heat up. Right, because it takes that many joules to heat up 1 gram of water by 1 degree Celsius. It only takes this teeny amount of joules to increase the 1 gram of gold by 1 degree Celsius. And that's what he's going to explain here, and then we're good. Awesome.
Now the energy is going to be the same. It's just that the water has a higher specific heat capacity, and so it's able to absorb more energy before it starts to change its temperature. And so did you learn to explain how heat exchange is due to kinetic energy?
Yes, he was just recapping. Okay, so let's pause on that one for a second. So from the, let me pull up the actual thing you guys are watching here. Okay,
So from the video, I wrote down a couple notes. The only thing that I just wanted to make sure was that was clear on that heat and temperature related. They're not the same. What's the energy? What's the unit of heat?
joules and energy, temperature unit for this one? Celsius. It'll say Kelvin occasionally, like you saw in his little diagram, it said K for Kelvin, but most of the time it'll be Celsius for us. All right, so let's change modes. You guys have a calculator? We're going to calculate one or two things first. I'm going to come back to the other video with the information related to endothermic and exothermic reactions. We talked about that a little bit yesterday, so I think that you're ready. We're going to calculate and we're going to add stuff to our foldable. What? So you guys have a colorful sheet paper in front of you, and I want you to fold it into 4 pieces. And you can even look on the link the document that you have open. There's a link that says, here's a link for the foldable. So if you want to pull that up on your computer, that's fine. But this is basically what we're going to be putting into 4 quadrants. So I'll show you a sample of my foldable. If I can find it. So I have one that kind of looks like this, which you make 4 little windows. So 1, 2, 3, 4. And you can see the link on the Google Doc with all the links on as well. So basically fold it so that you can eventually get 4 windows out of it. It doesn't have to be beautiful. It doesn't have to be perfect. I need 4 sections. Do you want to fold it in 4 corners? Do you want to get another sheet later and match it? Or marking prepared? Then this is what we're doing, okay? So we're going to start with 1 section at a time, and then we're going to do a question related to that little topic, and then we're going to do another section, and then another question. So I'm handing out the lecture notes, which has a lot of good things on it, like it's got your unit review for this unit, it has your problem set for this unit, and it has a couple notes for this unit. So you kind of give yourself a fold, and then it really doesn't matter. Really doesn't. It's going to make 4 spots. So basically, you're going to have 4 sections. Doesn't necessarily matter if it flips open or not. It doesn't necessarily matter if it flips over or not. Shannon, you can hold yours up. So Shannon has made, guys, look at Shannon. Shannon, close it for me. So he's got like 2 little doors, and he can just cut those in half, and there'll be 4 doors. You want to do it like that? Or, Lexi, hold yours up. You can do it like this, and you can fold it up into like a wallet and stick it in your pocket. Right? Doesn't matter. But regardless, please, on the first one, I'll get the extras in a second. On the first quadrant, upper left hand, put Q equals MC delta T. You want to make it pretty, get some of your colorful pins and stuff and such. If you're writing Q equals MC delta T, write that on the first upper left hand quadrant.
Is that all of them?
Say again? No, we're going to add a little bit more. Alright, so we're going to walk through the rest of this in a second, but that's the first quadrant. And like I said, I'm keeping it on the board, but it's also on the link on your Google Doc that you've been working from so far. So what we're going to put in each section is a description, the formula, then the description of the type of problem that equation will be utilized for, just to give us some context on like when we should use these equations. The definitions of the variables, including units, so that we're clear on what units describe which variables, because like in gases, I think we got those pretty quickly. These are a little different. And then a picture or diagram, something that would give us some indication of what the equation would maybe even look like in a real life scenario. And effective use of color. So I said start with color piece of paper so it gives us some effective use of color. So in the first section, I want you guys to write Q equals MCAT, and then let's go ahead and define the variables. And this is what we wrote down a little bit yesterday, but you guys were still working out your web quest. What is Q? What does it stand for? It stands for just straight up heat or energy. It does refer to energy, but energy is like a really broad term, not specific enough for us. So put heat, and then what unit goes with heat? Joules. Okay, so basically, guys, we're taking notes on our foldable, and then we'll do questions on a separate sheet of paper. Kind of doing active notes here. M stands for mass, and mass is generally going to be expressed in grams. Okay. C stands for specific heat, and you can just say specific heat, but I think you'll get mixed up with specific heat and heat. So I always say specific heat capacity, because it's talking about the capacity that this metal or this object has to gain heat. The capacity for heat, which influences how fast its temperature changes, which is what I wrote down from my video notes. Specific heat capacity. If it's got a low value, it changes in temperature very quickly because it doesn't have a very high capacity for heat. And if it has a high specific heat capacity, it doesn't change temperature very quickly because it has a high capacity for heat, so it doesn't change as quickly as something with a lower value does. This value is the big, like the R constant in gases, which is 0.0821 atmosphere liters per mole K. This is a big clumped up unit as well. Joules per gram degree C. And then temperature, delta T is what? I'm sorry, delta T is change in temperature. What unit would that be? Celsius. And again, one more time, how do we calculate that? T final minus T initial. Okay, so let's go ahead and apply this. This is called internal energy or internal heat exchange. It's talking about a scenario where it's just a an object that itself is heated or it's cooled and it causes a temperature change. So T final minus T initial. So I'm going to scooch forward. Oops. So this is basically what we're doing right here. Just this first section. So what you can write down is what that says in purple. You're calculating the heat. When the heat's not being transferred to anything else, it's just internal energy. So this can go on that same quadrant of the foldable. This is just like describing the scenario. So this is what?
That's all color around.
Yep. Just that section one. Yeah, we're going to put these other sections and other sections in forward. Okay, so if I'm calculating heat when the heat is not being transferred to another object, this is just an internal energy that's related to its temperature change. We're going to calculate that from the first section of the lecture notes practice. So we're going to start here in a second, but you should write this part on your foldable for me. So this will be a sample problem. This does not need to be in your foldable. You don't got that kind of room. I know some of my people write really big. You don't got that kind of room. We'll use it back for some, well, yeah, we'll use it back for something else. All right, so let's go ahead and look at, can I go forward?
There's that whole horizon.
All you're writing so far. Yep, just this first section. Okay, and if you didn't get that, I'm coming back to this slide about 3 or 4 times, so you'll get there. So let's go ahead and do the first question. Do you guys see this question on your sheet? Stainless steel. They're in there. There's like some place in the bucket. All right, so guys, do me a favor. Read and write down your givens. Read and write down your givens. So, a piece of stainless steel weighing, what is this? What variable is this? Mass, thank you. Mass equals 1.55 grams. This is a sample question. Write this next to your, someplace else on this note paper. All right, so I'll wait on you guys. You guys can read it and write down your givens. And then tell me what we're solving for as well. Alright, JT, what was one of your other givens?
141 joules.
Alright, what variable is that? Q, right, so you got your foldable, you're seeing heat, you see the word heat, you should recognize that as Q. Q is 141 joules. Zach, what's another variable given to us?
170 degrees Celsius.
And so that's our delta T, right? So it says the temperature's changing or it increases by that. So we're saying delta T is increasing, so it's a positive value, 178 degrees Celsius. Erilyn, what are we solving for? So, which is C, good. So we're solving for the C value. So what you're seeing now is that you know the formula Q equals MC delta T or Q equals MCAT. You see the variables. You should visualize the formula in your head. Solve for the variable you don't know. Plug it in. We're done. So the formula is Q equals MCAT, right? So how do I get C by itself? Divide by, I like to say divide by Matt. That's my husband's name. So when he listens to this, he'll go, oh, she's talking about me. Okay, so C and delta T, gone. And then Q divided by M and delta T, that will give us our final answer. So C is equal to Q over M delta T. I'm just rewriting this for my own purposes. But at this point, we're good to plug in, right? No values need to be changed, no units need to be changed, we're plugging in, that's it. So Q is 141 joules divided by 1.55 grams, which is our mass, and our 178 Celsius, which is fine for temperature unit for thermochemistry. We get C is equal to, whenever you're ready. So again?
0.511.
0.511 what, Joey? What are the units that remain? Look on the board, look on the board.
Divide like grams. Celsius.
Great, so do you see all these units? They remain because nothing cancels. You keep them all, right? So joules per gram degree Celsius stays with us as the entire unit that describes specific heat capacity. I'm gonna scroll up a little bit for you guys. So that's an internal energy calculation.
So we calculated the specific heat capacity. There are a couple of the formula sheets, reference tables floating around the room. Is there one close by enough that you guys could look at one? In your little buckets maybe? There's probably at least one or two per day. So I want you guys to look at the specific heats. This one. Look on the metals, which are on the upper left-hand side. If you had to identify a metal that was close to that specific heat, what would it be? You see the table with the metals and specific heats? Who would it be close to? Titanium? That's what I would guess, because that's the only thing I have close enough. All right, so basically, we could have an unknown metal. We could identify the heat and temperature change that's associated with it. We could identify the specific heat capacity and then look at a table that are constants that have been established by scientists. And we identify the metal. And so I'm just going to say a picture for this for your foldable. You're going to have to be creative, but there's a piece of metal and it's absorbing heat. And the temperature is going up. Oops. Something like that. It doesn't have to be pretty. Mine's beautiful, I know. But we'll come up with a picture for that one shortly.
Wait, you want the same problem?
It does not need to be in your foldable, no. That's going to be only this information here. Description of the type of problem or scenario, which I'm giving you as I go. Definition of the variables, which I'm trying to do as we go. Drawing a picture or diagram that represents something about the equation. That's got to be a little bit on your own. And effective use of color, you got this. Okay, so now let's do the second section. Second section is, let's do this one right here. We're going to pop that one over here. Q equals Q. And this is really tiny. I know it says negative Q of surround our system. So it's negative Q of system equals positive Q of the surroundings. Something like that. And that's going to be on the next slide as well. It's a little tiny. This is my like just instruction sheet for you. So now we're talking about objects that are exchanging energy. So like a coffee cup in your hands, who's going to get the energy? Let's say it's hot coffee. Who's going to get the energy? Your hand. If iced coffee, who's going to get the energy? The coffee. Okay, so this is the information. I'm going to be quiet for a couple minutes. This is the information. You can abbreviate where you need to. That should go under that section of the foldables. And I like foldables because they keep all your information in one spot. And so just bear with me if you're not a foldable person. I'll look on this one first. Hopefully they're not played out like West. Oh. That one should look maybe vaguely similar to what you were working with yesterday with me on the board. When you get down here to the MCAT equals MCAT, where you were looking at heat exchange between two things. So we talked about this pretty extensively, I think now. There's this thing called energy. It's just passed around to different objects. It's not destroyed. It's not created. So to track that transfer of energy, we need to always identify one thing, just one thing as our system, which a lot of times is going to be just like a piece of metal or a rock, or like a coffee cup on our hands. The coffee would be the system. It's something that's mostly dealing with our chemical reaction or chemicals or a compound. So the system many times, in our examples that you'll see on paper, it's going to be just called a metal, and we heat up a metal, and that's what your simulation included. But everything else around it's called the surroundings, and the surroundings can include a cup, a thermometer, the air, your hand, just everything around it, which makes sense. It's the surroundings. And so what we do is we have to identify who's gaining energy and who's losing energy. Not all the time is our system losing, not all the time is our system gaining. So our surroundings gaining. We have to kind of look at the question and make a choice. So I just said put a positive or a negative sign based on who's gaining energy or based on the transfer at hand. It's going to change every single scenario. But a good example of this, a good picture, I'll put the picture on the next slide, is something that we call a calorimeter. What kind of word do you hear in there? Calorie, right? We talked about calories briefly yesterday, but a calorie is a unit of energy. And so a calorimeter is a device, just like a meter. Where have you heard meter or metry before? Thermometer, which measures thermal energy, that's heat. What else? Stoichiometry, right? We're measuring the chemistry app. We're measuring moles and grams and atoms. Where else have you heard meter before? Okay, so like an actual meter, like a length, a unit of length, like a meter stick. So this just means measure, right? But we're measuring calories, we're measuring energy. We have a device for that, but we have a really cheap device. It's called a styrofoam cup. Why would I want to use a styrofoam cup to measure heat exchange? So what's the word set for that? It's an insulator. Styrofoam is a great insulator, right? That's why they sell those big, huge, like gulp cups that are styrofoam cups at the gas station. They're big, huge styrofoam cups because it keeps it really well insulated, so your drink stays colder, your drink stays longer, or at the particular temperature you want it for longer. So let's do a question related to this, and I'll draw a picture on the next slide as well. So there's my cup. This is my calorimeter. I'll kind of make this a little bigger for you. This is like a super cool drawing of one. Let me show you my artistic abilities and show you one of these. Here's my cup. And sometimes it's double walled, so it's really great insulator. I put some water in it, and I drop a piece of metal in it. And then, I do have to have a thermometer. Is that a thermometer? Something like that. Thermometer in it, okay? So this is a system and surroundings combination. So whatever you do, make sure you know one of them is the system, and one of them is the surrounding, and that together is going to be kind of holistically considered. So it doesn't have to be beautiful. But you got a cup, and you got a rock in it, you got a thermometer sticking out of it. Okay. My little artiste. Okay, I'm going to go to the problem now. This problem is under the second section. So we just did the first, if on your paper, if you're looking at the lecture notes, we just did the first one from 1 through 4. Now we're going to do number 1 from the calorimetry section. So what you can imagine is now we're going to have energy relationships between the two system and surroundings. We're going to have information about both the system and the surroundings. So we have a lot of data to record here. So you guys read and tell me what you first realize are the two objects. What are the two objects here? Metal and water, right? So I told you that's generally how it's going to be. I always set up my table of information for metal and then separately for water so that I know which mass is for metal, which mass is for water, which specific heat is for metal, which specific heat is for water. It's very specific. So, question, what is the specific heat? What's it asking for? C, thank you, value C, for the metal. So I'm going to say question mark C. And what does it tell us about the metal so far? So mass, right, M, mass is 50 grams. That raises 100 milliliters of water. 100 milliliters. Have we been putting milliliters anywhere? No. I know that's a volume unit like in a liquid solution, but this is water, right? We know something special about water. What do we know? The what? We know it can be displaced, but that's not really necessarily necessary here? Okay, the density of water, that's what I was looking for. The density of water is 1 gram per 1 milliliter. So if I have 100 milliliters, how many grams do I have? 100 grams. So because I can't put milliliters in my mass section, so I have to put 100 grams for water. Okay, and it says the water in a calorimeter is raising from 34 to 36 degrees Celsius. So that's delta T, right part of the water section. So what's my delta T for water? It is 2 degrees. I am going to say it's 36 degrees, which is T final, minus the 34 degrees, which is T initial. That's going to give me 2 degrees Celsius. Because I always got to think about that T final minus T initial, because occasionally it doesn't matter because you'll get a negative value. Like now, okay? So the initial temperature of the metal was 95. The final temperature of the water and the metal is 36. So before you tell me that value, why are they both stopping at the same temperature? What's the word for that? Thermal equilibrium, right? They have to come to the same temperature at the end, because if they're not at the same temperature, the heat's going to keep flowing to one from the other, and we're not done yet. So they should end at the same temperature. If it's not, you got a problem. So at this point, I have 95 degrees Celsius initial, 36 final. How do you get your temperature change for metal? Subtract what? So 36 degrees Celsius minus 95 is what? Say again? Negative 59, right? So we have negative 59 degrees Celsius change. Okay, what else are we missing from our water column? Specific heat capacity. On your reference table that's kind of floating around nearby, look at the upper left-hand side again, and tell me what the specific heat capacity of liquid water is. Specific heat capacity of liquid water. Thank you, 4.18 joules per gram degree C. Now, you're going to get that reference table, or at least some of those values, so I just want to make sure you know where they are whenever I need to give them to you. So, now we have everything for water, with almost everything for metal. This is the situation now where we're able to say Q is equal to Q, but I don't have Q for either one of them. So there's two ways to solve a problem like this. You can take all the information for water, and you can find Q. And if you take all the information and find Q, you're good to go ahead and set this Q of water equal to the Q of the metal, and then backtrack and solve for C. I'm a fan of just getting it all done in one step. And that's where I told you yesterday, MCAT equals MCAT. Do you remember that? Mm-hmm. Yeah, a little bit. So basically, if the Q of the system and Q of the surroundings have to be equal, who's losing energy here? Who's going down in temperature? The metal in this case, right? So it's got a negative value for temperature. So this is going to lose energy. It's going to have a negative value. So instead of doing Q equals Q, I'm going to do MCAT equals MCAT because they are equivalent. So MC delta T for the metal equals MC delta T for the water. However, the metal being negative energy has to keep the negative here. So you remember doing this yesterday? Mm-hmm. What do we do from here? Or what do we need to do from here to solve for C of the metal? Mm-hmm. So I could straight up right here plug in my values. I'm a fan of isolating the variable of interest and then plugging so that I don't have to double plug. So I need to solve for C over here, correct? So I'm divided by what over here? Negative, right? Negative M and delta T of the metal. Divided by negative M delta T of the metal. And that negative in the end will cancel out. I promise you it will cancel out. So just make sure that in the end you don't have a negative C value. There's no negative specific heat capacity. You can't lose energy to increase 1 degree Celsius. It doesn't make any sense. So in the end it will cancel out. So this negative here, metal mass, and the metal temperature cancels. So now C is equal to this big guy, MC delta T for the water, divided by negative M delta T for the metal. So now that everything's really well organized over here, it's easily plugged in, canceled out your units, and then calculate. So go ahead and plug in your values and calculate. You should have this in front of you, so I'm going to write some up here too. So whenever you're plugging your values in, you should realize that the grams and grams on top and bottom will cancel. The Celsius and Celsius on top and bottom should cancel. What units are remaining? The whole shebang, right? It's joules per gram degree C. So that's going to be our final unit, which makes sense. That's what specific heat should be recorded in. Does anybody have a value for me? Say again? 0.2843 sounds lovely. Anybody else? 0.2? Say again? Yeah. Awesome. So what we're noticing is that metals generally have really small C values because they generally lose energy change temperature very, very quickly. If you heat up a metal pot, it's going to heat up pretty fast. You cool down some aluminum foil, it's going to cool down pretty fast. Say again? Say again?
Wouldn't that be considered negative?
The specific heat capacity will never, ever, ever, ever be a negative value. The heat can be negative and the temperature can be negative, but that itself is an inherent quality about it. It's not a negative value. Good point. So this is always going to be positive. All right, so that one's a little bit more math, but it's not too hard, right? You feel okay about that? All right, next section of your foldable now, okay? I'm doing one of each one to give you guys a chance to see everything first. So, let me show you where this goes. So now we're going to do, I'm going to do this lower left-hand side. So this is Q is equal to moles times delta H. And I'm actually going to show you another equation to put there as well, because occasionally, so these delta H's, these enthalpy values, those occasionally are given in joules per mole or kilojoules per mole. But what you'll notice on this reference sheet, so if I give this to you in the future on this section, it says like on the upper left-hand side, it says heat of vaporization and heat of fusion. Those are actually established as grams or joules per gram. So if I give you grams, I'd like you could use that if you wanted to. So another equation that could go here could be Q is equal to mass times delta H. It just depends on what information or what units are given to you. So either one of those could work. And before I move on here, I'm going to let you watch the other video that I didn't show you with endothermic reactions and exothermic reactions, because it's going to be related to this section. So give me a thumbs up when you're good here. All right. And
Hi, it's Mr. Anderson, and this is Chemistry Essentials video 33. It's on endothermic and exothermic reactions. If you understand that therm means heat, and exo means to exit or to move out, it's pretty easy to break down these reactions. So an exothermic reaction would be one where heat is being released from the reaction.
so the question was, can I draw some foldable? If you turn it on the back of your foldable, if you have space, you can draw the two graphs that he's getting ready to mention. And I'll tell you when, and I'll draw them on the board too. That way you have a chance to kind of have everything in that one spot again. Because thermochemistry is going to move, we're almost done with thermochemistry after today. Thermochemistry is a flash. Just two basic calculations, and then you move on.
So a thermite reaction right here, you can almost feel how hot that is a reaction where we're releasing energy, releasing heat from the reaction itself. And likewise, if we have an endothermic reaction, that's going to be one where the reaction is taking in heat. And so in a cold pack like this, there's a combination of water and ammonium nitrate. That reaction is consuming heat, it's taking it from the surrounding, and so it's going to feel cold over time. And so you really have to understand what is the system and what are the surroundings. And so in a reaction, the system is going to be where the reaction is taking place. So in the chemicals themselves, and then the surrounding is going to be outside of that. So if we have a change in heat, that's either going to be an exothermic or an endothermic reactions. Now in the lab, we can't really see at the level of the atoms, and so we have to view it macroscopically. And we do that by simply measuring the temperature change. And so in an exothermic reaction, we're going to find that heat is being released from that reaction to the surroundings, and in an endothermic, it's actually being absorbed. Now a really neat way...
Okay, so I'm going to kind of give you the information I think is important. So I said exothermic reactions and endothermic reactions. We're going to have a graph for that in just a second. I have a little axes here already drawn. Then he specifically said, exothermic reactions release heat, right? So we know, I'm going to put release heat under my exo section. Release heat. And if I release heat and I lose my energy, we call that a delta H. Delta H, plus or negative? Negative, right? That's a negative delta H. Endothermic reactions, we're going to draw a graph for that in a second as well. They absorb heat, and that has a delta H of positive. So he also mentioned one thing at the very beginning. If I had, for example, if I have a hot pack in my hand, you guys read the article on hot packs. If I read the hot pack, or if I have a hot pack, how does it feel to me? It feels warm to you. You are the surroundings. It feels warm to you. Energy is being given to you. So when I'm releasing heat, I'm going to put right here, it feels warm. I don't want you to think about right now how the temperature changes, because if a lot of times when students get mixed up, they'll go, oh, I release heat, I have less energy, I drop in temperature. No, I actually am rising in temperature because is the thermometer a part of the system or the part of the surroundings? Surroundings, just like your hands are part of the surrounding, it feels warm. If your hands feel warm, your hands are actually doing what in temperature? Raising in temperature, right? So if it feels warm, that means the temperature goes up. T goes up. And a thermometer would read that as going up. Energy would be going up, so energy would be coming out of the system. Thermometer would be reading higher temperature. So that's one point that everybody gets mixed up, and it's hard to rationalize and know why. So if I'm absorbing heat, if the system itself is absorbing heat, like an ice pack, how does it feel to you? Cold. Okay, so it feels cold. So if it feels cold, what's happening to the thermometer's reading? It's going to go down. So the energy is being used up, so temperature goes down. Energy is being used up, it's absorbing the energy, it's gone. That's why the energy is like disappeared essentially, but it's actually being consumed, it's being used up. So absorbing heat does not mean the temperature goes up. Absorbing heat means it's used up and the temperature will actually go down. So that's one of the biggest misconceptions. Let me start him back up. We're going to just finish this real quick.
To observe this is to use a model, is to use a energy diagram like this. And so the way it works is that the energy progress will be going along the x-axis, and then the amount of energy in the reactants and products is going to be displayed. And so in an exothermic reaction, what you'll see is a downhill reaction. In other words, the reactants are going to have more energy than the products. Now, where is that energy going? Where is that heat going? It's going to the surroundings. And likewise, in an endothermic reaction, the reactants are actually going to have less energy than the products. And so they're consuming that energy. And so let me give you an example of that. Here's that exothermic reaction again. We've got a thermite reaction where we're taking iron oxide and aluminum, and we're making iron and aluminum oxide. Now, this is a really intense reaction, and it's actually it provides the oxygen in this form of combustion. And so this should be able to work even underwater. But if we were to look at the energy diagram of this over time as it progresses, we'd find that these reactants...
All right, so draw that for yourself. So I'm sketching as well. It starts off with a reactants with a fairly high amount of energy. It doesn't really matter where it is, but it's higher. There's a little hump. And then the energy of the products ends up lower. So put R for reactants, because reactants start with a high amount of energy. They go through this little system of some energy is being applied, so it's going up high. And then overall, the after effect, the products end up low because energy was released. Energy was released, so that way that's why the products have lesser energy than the reactants do. Can I go forward?
The iron oxide and the aluminum have a higher energy. In other words, there's more energy locked in those bonds than we're going to have in the products. And so we can see this as a downhill reaction. Now, what's going on? Why do we see this increase in energy here? Remember, we have to start pressuring those bonds, put a little bit of pressure on it before we can actually have them break apart, and we get that exothermic reaction. And we call that a activation energy. So you're going to put a little bit of energy into the system, but you can see that we're going to net energy coming out of that. And so that's going to be measured in heat coming off that thermite reaction. Now, if we look at an endothermic reaction, again, this would be like solid ammonium nitrate, and we're just combining it with water, so we're going to make ammonium and nitrate ions. In that case, what we're doing is the reactants are actually going to have a lower amount of energy than the products. And so you can see here's our activation energy, but this is an uphill reaction. In other words, it requires energy, it requires heat. Where is it getting that heat? It's getting it from the surroundings. And so when we're measuring...
Let me just pull him back a little, you guys can see that graph. So this graph looks like it's flipped, basically. And so the reactants start off low, and the products end high. I'm going to show you my drawings so you can see that too as well. So the reactants start low. There's a large activation energy. So the energy it takes to get from where the reactants are up to the tippy top. I'm labeling that EA activation energy, or energy of activation. And we haven't talked about that extensively, but we will much later. It's just the energy you get from reaction start. It's like a spark. And so the products are going to end up higher. And so the contrast here is that the reactants, there's more energy in the reactants than the products in an exothermic reaction, meaning heat was released, it's released. And the endothermic reaction, there's more energy in the products than the reactants, meaning energy was absorbed as the products formed. So I'm leaving all of this right here for you. But I think it's important to have on the photo because all this will go together. Alright, so before I move on to more calculations, let me pause. You guys need a chance to kind of see if you can do this by yourself. So do the second question from each of the sections we just did. I did question 1, you're doing question 2. So work in your teams right now. Take 5. You're doing 2 and 2. So 2 and 2.
Heat. Where is it getting?
Sorry. And I will say you will need the reference table to look for iron. Is it iron number 2? Specific heat capacity of iron is 0.449. 0.449 if you don't have a reference table nearby.
So you take all of the like given with the game and you plug it into the equation, but like the change in temperature is from 20 to 46 to 20. And then you just multiply them together because you're looking back here. Do you have like what C is? It's the it's like on this piece of paper. It's point
1 calorie is equal to 4.18.
Those two numbers. Uh, 359.2.
Alright, are we okay on number 1, guys? Give me a thumbs up if you're through number 1. Alright, so on number 2, I just had somebody ask me what the calculate or the conversion factor between calories and joules are. For water, this is only for water. Well, actually, no, this is true for everything, but just by chance, water's specific heat capacity is 4.18 joules per gram degree C. It's also 1 calorie per joules degree per 1 calorie per gram degree C. So these two things are equivalent for water. So what you'll notice is that charts units calories, not joules, and so that's why that matters in this case.
So you just like the 4.18 calories.
Either that or I would just take this calorie. Oh no, I would just take the 1 calorie and use that for the specific heat of water. Since this one's in calories, I think we should do the whole problem in calories versus joules.
So you just do 30.49 so you find change temperature from that one.
Oh, okay.
And subtract 3.4 for water.
Alright, give me a thumbs up if you've made it somewhere close to this, maybe farther at least. So the calories given to you made me think about twice putting the joules on the water side, so that's why I just said the conversion between calories and joules is 4.18 joules is equal to 1 calorie. So took water's 4.18, just made it into 1 calorie, so these two units would agree. And then as you're looking at your temperature initials and temperature finals, you should realize that the metal is dropping in temperature, so what's its value for delta T? Negative what? 55.2? 8, my bad, okay. So negative 55.8, what's water's delta T? 6 degrees Celsius, because it has, and this is a negative because it dropped energy, this is gaining energy, so that's going to be a positive value for the delta T. And so we got the mass of water to be 100. The question is, what's the mass of the metal? Are you comfortable setting up from here? What's the equation, Jake? M of the metal. Okay, so you're already going ahead and tell me the last part of the setup? I'm good with that, okay? This is referring to what then? All of this. The metal or the water?
That's the water.
Right, all of this information is referring to water, because, you know, we got 2 M's, 2 C's, and 2 delta T's. It's important to know which one you're talking about. So that's water divided by of the metal, right. Okay. So after you had this, he achieved this by first doing Q equals Q, and then MCAT equals MCAT, and then pulling everything away from the M so that you could solve for the M individually. I'm trying not to insult your intelligence on your algebra, but I know that some of us are like, we know how to rearrange formulas, and some of us are like, I haven't rearranged formula in like 2 years. So just make sure you ask me questions on rearranging your formulas. But this is how you set up, and then all your units will cancel except for mass. Hopefully, but how did we get here again? He said Q is equal to Q for the metal versus water, because this is an internal energy exchange, or a energy transfer. And so MC delta T equals MC delta T, since we're basically substituting MC delta T for Q on both of these accounts. And then after that, once you looked at your variables, you're looking for the M here. We basically isolated this M right here. It's by itself now. All right, so let me stop there for a moment.
If you're ready to move on, you can move on. I'll see you on. If you're ready to move on. I'm going to do one other type of question in just a minute, okay? Yeah, so one of these has to be negative because of the variable of the metal losing energy. Thank you. But the negative will cancel itself out due to the nature of how the mass won't be a negative value, so we won't have a negative at the end. So if you're going to move on to either 3 or 3 on the second one, well, some of us are finishing this one up. Yeah, 326. What did you say, Jacob? Jacob, 326.83. That's a weird number.
Yeah, because there's more metal than water.
That's why you need that.
Yeah.
I got you. I looked at my initial alert versus my final. Alright, give me a thumbs up if you are okay to move on to the next question. Come on, here. Oh, reset section. These are done, things are so sharp.
Oh, did you have those?
I need like child cushions there. Wow. All right, we're doing one more. One more. Last one for the day. I got 12 minutes. Here we go. So on the flap on the folder, we'll get to that information shortly, but you wrote the equation down, and we'll talk about what that means in a second. So transition back to me. If you're working through your section for a second, if you're undivided attention. This is a question we're going to attempt together, okay? So you guys have seen a heat curve before. So I want to see, let's see if you can do, not this one yet, do this one second. We're going to do this one. Is this one on your paper? Number 3?
it's going to be number 3 down. Actually, I lied. It's 4 under heat of phase change. Number 4 under heat of phase change. Do you see that? Okay, so draw yourself a heat curve, and we're going to label the pieces of this. We're going to talk about how to do each of the pieces together, though. So this is not on the foldable. This is just on your notes that you're taking as for calculation practice. So the question is, first, how much heat is required? So we're looking for Q. How much heat is required to change? And I see this number, and that to me says mass, right? So mass is equal to 52.9 grams. And then it says of ice. Well, ice is not liquid water. Ice is a special type of water. It's a special form. And then it's going to go, it's starting off at negative 15 degrees Celsius, and it's going to go all the way from ice, take a journey all the way to steam. So we not only have temperature changes, but we have phase changes as well. So this is kind of the pinnacle where you have multiple types of heat that multiple ways that heat are being used to change a substance. So it's being used to change the temperature of a substance, and then it's phase changing. It's being used to change the temperature of the substance, and then it's going to be used to phase change, and then it's going to change the temperature of the substance one more time. Because at this point, we're going through 2 phase changes. And on your graph, I want you to label the points as here. Negative 15 degrees Celsius, because that's our minimum temperature. And then what temperature does water, because this is ice, right? This is solid ice right here. What temperature does water start to melt? 0 degrees Celsius. So that's going to be a 0 over here. Okay? Then we're going to go ahead and let it transition. It's going to melt here. And then we're going to do what? Turn all the way to... So solid's gone all the way to form liquid, right? So now we're in liquid phase here. I'm going to put an L there for liquid. And it's going to be, after it's melted, it's going to heat the liquid, all the way to what temperature? This is 100. Now this is water, right? This would be a different value for other substances, but we're using water because we know it very well. We know the values of the change phase. And then the liquid's going to eventually get so hot it can't stay liquid anymore. It's going to phase change here. What is this phase change called? Vaporization. So I'm going to put vape there. I'm going to put melt down here, but that was another word we used yesterday, day before? Fusion. Thank you. I'm going to put fuzz, fusion right there. Okay, so we've gone from negative 15 to 0, change phase. 0 to 100, change phase. And then we do what? Peak out where? What's the top temperature it told us in the problem? 200. Jake, what are you doing? Oh, okay. I was like, please don't be videoing me. Thank you. All right, so in this case, I have I have 5 Qs that are associated with this entire process, and you can see them as the sections of the graph. 5 Qs. But a couple of the Qs are calculated exactly the same way. It's just we are referring to different states of matter at that point in time. So let's start right down here at the blue section. This is our solid. I'm going to call this Q1. So if you're going to label your graph so that you know what your work pertains to, that might be important. So I'm just going to start working right here. Q1 is equal to something. But as you notice, the temperature is changing in this section, right? So which equation would be used? The equation you wrote down first, which was Q equals MCAT, or the third equation you wrote down, which was Q is equal to moles times delta H. So there is a temperature change here. Which equation has a temperature change in it? MCAT. We have to use the one that has temperature change in it. So we're going to use MC delta T on this first Q. What's the mass? 52.9. Thank you. What is the specific heat capacity of ice? This is not one you know. You need to look on the reference table. Look for ice. Say again. 2.05. Thank you. 2.05 joules per gram degree C. What is the temperature change that's occurring in this ice section? 15, right? 0 minus a minus 15 is just positive 15, right? So we have now just looked at the graph, pull the information off. I'm just plugging in here. I'm not even going to calculate yet because I know you guys can calculate. All right, so now the next section, I'm now here. Notice that the temperature changes. There is no temperature change. I cannot use an equation with delta T in it. What would be the appropriate equation on this section? Okay, either, and I want to write this down in here, I can do Q is equal to moles times delta H diffusion,
Or I can do mass times delta H diffusion. And I'm going to actually right now encourage you to do the mass one. It will work either way, only because you have a reference table in front of you. What does it say for H diffusion on the reference table? It's going to be kind of in the similar section. So it says like heat of fusion. 334. I'll write that down right here. 334 what? Joules per gram. So if it's already in grams, why do I need to waste my time taking grams to moles and then finding another variable? I have the delta H diffusions. It's like 6.01 kilojoules per mole. But I'm going to stick with that because it's on the reference table. So I'm going to say Q2, which is this green section here, which is a phase change Q. The Q that, or the energy it takes to melt, is mass times delta H of fusion, because it is melting. There's just two variables here. What's the mass again? What's the mass of our substance? 52.9. And this variable, this value that I just pulled off the reference table, is going to be what I plug in here. So 334 joules per gram. What units cancel? Grams, we're stuck with joules, which is good. This is in joules, this is in joules, we're doing great. So, you see what we're doing now? We're doing step by step. So we've now taken the ice from -15 to melting. We've melted it. Now we're going to take it from here to here. What equation would apply on this red section here? Ym cap. Because there is a change in temperature, you must account for that change in temperature with an equation with delta T. So this section, what is my delta T? Right, you're going 100 minus 0, so the delta T here is 100. So Q3, which is my third Q I'm using, the mass is still the same, yes. What about the C value? What about the C value? Yes, that's now liquid water, right? So we look at the reference table, we see the new C value. So this is 52.9 grams, 4.18 joules per gram degree C, which is representing liquid water, and our temperature change, Lexi said, was 100. Whew, we're almost there. We have melted ice, or we've heated ice, we've melted ice, we've now heated our liquid water. Now our liquid water is going to do what? Change its phase. And now which equation do you think is going to be used, since we're now at the flat spot again here? Mass times delta H.
Attention students, don't forget tonight is basketball game versus Northwest Cabarrus. It is here at home. First game begins at 4 o'clock, and it is a whiteout tonight. Come and support your Chargers. Thank you.
Bye, Jay. So, last bit, I'm going to write this down because you're going to see a question like this later. Mass times H of vaporization. You'll plug your variables in there. The mass is still the same. The vaporization is still the same. That last step I'll do on Monday, but it's the last step, which would be our last slant. That'll be Q5. And since it's a slant, the temperature is changing. So we'll be in that there. So I'm going to ask that you log off your computer to make sure you can have them systematically if you use.
Come on.